Alright guys, so let's go ahead and get started on this review. Display settings, well, presenter, there you go. And let me get a highlighter. Let's go with orange. Wait, that's a pen. Highlighter. And make it orange. Alright, so here comes the review. So the circulatory system, whenever we refer to the circulatory system, we're referring to the pulmonary and cardiovascular system. The purpose is to receive oxygen, give it to the tissues, remove carbon dioxide, which is a waste product of our metabolic demands, and then regulate body temperature, right? It's important to remember there are two major adjustments to blood flow during exercise, right? So we increase cardiac output. This one is obvious. We increase heart rate, we increase stroke volume, but we also redistribute this blood flow to active muscle. Okay. Next, the anatomy of the heart. So, right, we have arteries being uh, vessels that carry blood away from the heart. Then we have arterioles, which are the smaller version of the arteries. They're also known as the resistance vessels. We have then from there we go to the capillary beds, right? So at the capillary, it's where all the exchange of nutrients happens. And then once it passes the capillaries, it goes into the venules and veins, which carry blood towards the heart. Next, right? So let's look at the order at which we travel through the heart. So if we start at the right atrium, we go down passing the tricuspid valve into the right ventricle, right? Once it pumps, we go past the pulmonary semilunar valve into the left and right pulmonary arteries, right? So the one of them goes to the left lung, the other one goes to the right lung, and that is into the pulmonary circuit. I'll just put pulmonary, right? So it goes pulmonary circuit, comes back down the pulmonary veins, one on the right, one on the left, right, into the left atrium, passing the bicuspid valve into the left ventricle. It contracts, passes the aortic semilunar valve into the aorta, going to the systemic circuit. Sorry for that. But luckily for you guys, it's all written out right here. So don't have to rely on my handwriting. Next, we have the myocardium. That is the most important layer of the heart, at least for this class. Um, it is essentially another word for the heart muscle itself. It receives its own blood supply, and we like to call, or they call a heart attack, a myocardial infarction. That's whenever the coronary arteries get blocked and lead to heart damage. Remember, exercise training helps protect against heart damage. And to what extent, right? So remember, people who exercise regularly only have a 20% chance of getting heart damage as opposed to 60% that happens in the untrained population. Now let's go back to this one. Right, so what are the biggest differences between uh, heart and skeletal muscle? Oh, geez, that did not work the way I wanted it to. Yeah, that was supposed to highlight it. So, one of the big ones is single nucleated versus multiple nucleated, right? So, oh, geez, let me delete. There you go. Okay, yeah, so heart muscle, single nucleated, skeletal muscle, multiple nucleated. This is so it sends a signal across the heart and they contract at the same time. Intercalated disc, right? This helps send that electrical signal to the rest. So they're essentially like connected like this so that the signal passes a lot better than being connected in line like muscle is. Um, Next, right? So these have no satellite cells to them. And that is important. Let's see. Right, so this is for the electrical signals. Next, the cardiac cycle. So the contraction phase is the systole. Let's see what's next. Arterial blood pressure, right? So we have systolic and diastolic, systolic being whenever we contract, and then we have the difference, and that is pulse pressure. Let's see next. Right, so remember the heart and the signals that get sent to the heart are set up by the sinoatrial node, otherwise known as the SA node. It is in the right atrium, right? So this is the pacemaker, causes the contraction that is passed through the AV node into the ventricles. And next. All right, so we're able to measure these electrical signals using ECG, right? So we have the P wave, which is atrial depolarization, QRS is ventricular depolarization and atrial repolarization, and T wave is ventricular polarization, right? So be familiar with which ones are those. Uh, okay, regulation of heart rate, right? So the heart rate is stimulated by two main nerves. We have the vagus nerve and the cardiac accelerator nerves, right? So up to about 100 beats per minute is where the vagus nerve is causing a decrease in heart rate, right? So this maintains you at rest. Anything above that is caused by the cardiac accelerator nerves. Next. Um, Actually, I don't think we need this, but I'll double check in a bit. Regulation of stroke volume, right? So stroke volume is essentially how much blood you're pumping per beat, right? One of the biggest factors on stroke volume is end diastolic volume. This is how much the ventricles are filled at the end of diastole. We usually increase this with venous return, which we'll go over in a bit. We also decrease aortic blood pressure. So the aorta, if there's lower blood pressure, it makes it easier for us to pump blood out. And then lastly, ventricular contraction. The strength of that is caused by epinephrine and by the cardiac accelerator nerve, making each contraction harder. One second. Right, so end diastolic volume. Right, so end diastolic volume is how much blood there is in the ventricle before it starts to contract. If you remember, about 70% of the blood that flows into the left ventricle or right ventricle to flow in freely. The rest is then pumped in by the atrium, right? So whenever we fill that left ventricle by a lot, uh, there is a more optimal length of contraction, right? So that's called the Frank-Starling mechanism because it's filled with more blood, it's stretched out, and it can have a more forceful contraction. Be very familiar with venous return. So this is going to be your written out question, right? So venoconstriction, the veins become smaller. The vein system is a very low pressure system, so if we increase the pressure a little bit, it'll cause blood to flow a little bit faster. Next is the skeletal muscle pump. So whenever you're contracting, they force blood from, like, say, your legs towards your heart. Remember, they have a one-way valve system, so if you push it up, it won't come back down. So as you contract and squeeze the muscle, make it larger, pushes up the blood and prevented black flow because of the one-way valves. And then lastly is the respiratory pump. Every time you breathe, you decrease thoracic pressure, causing blood to flow from an area of high concentration to an area of low concentration or low pressure. So this one written out question. Okay, next um, here, so blood flow, right? How to determine blood flow? So the degree and pressure change, right? So how much there's a difference between one side of the pressure and the other. And then resistance is one of the bigger factors, right? If there's less resistance, we can flow blood more. And resistance is mainly dictated by radius, right? Because length we can't really change. Viscosity we can change, but not as rapidly. So radius being dilation, right? So that is very important, probably the most important factor right there. Oxygen delivery during exercise, right? Important to remember this whole redistribution thing. We can increase heart rate and stroke volume, but now we need to redistribute that blood accurately. Next, increase in stroke volume, right? So cardiac output is increased by heart rate, but your heart rate's already kind of set. There's nothing we can do about it. But stroke volume is how we get better. And in a normal person who is untrained, their stroke volume caps out about 40 to 60%, while in a trained subject, it increases till about 100%. Check. Um, yep, so stroke volume once again, 40 to 60% in untrained subject, and it does not plateau in trained subjects. Sorry. So in untrained subjects, it plateaus at 40 to 60, and in untrained, it does not plateau. Here is an example. One thing to note is that, no, it's not here yet. Okay, so auto regulation of local blood flow, right? So, uh, right, this is how we redistribute the blood. So, auto regulation means that it regulates itself. So, skeletal muscle, whenever we contract it, causes a release in a difference in O2 tension and CO2 tension, causing a release in nitric oxide, prostaglandins, and adenosine, which are vasodilators. So that's how they dilate themselves. Right, so incremental exercise, this means as we increase intensity, so as we're going higher and higher in intensity, you'll see that heart rate goes up, blood pressure goes up too, but only systolic. Diastolic blood pressure should not change much. And then, yeah, so that's about it for that one. Boom, boom. Arm versus leg exercise. So in arm exercise, you will see a higher heart rate compared to leg exercise. So high, low, and then this is higher heart rate. Prolonged exercise. As we start to exercise for longer and longer periods of time, we'll see that. Here, one second, let me double check some stuff. We'll see what's called the cardiovascular drift. So as we start to sweat, as we start to work harder and harder, will cause a decrease in plasma volume, causing our heart to have to beat harder to move the blood uh, the same way as opposed to whenever there was more blood volume. So central command theory, right? What this means is that the drive to start at the beginning of exercise comes from higher brain centers. So this does not come from like your mechanoreceptors or any other part of your body, but rather a higher portion. Next, respiration during exercise. Oh, actually, one second. Let me go back to this portion. Right, so beta blockade of the heart. So what do beta blockers do? They compete with epinephrine and norepinephrine. So what they'll do is they'll reduce heart rate and the contraction. Yeah, so those are the things to know. Very common medicine. You'll probably see it here or there if you do end up working in the fitness field. All right, so now on to, yeah, okay, we covered everything there. Now on to chapter 10. Yeah, sorry I'm all over the place. I'm trying to make sure I cover everything. Right, same thing, very similar to the cardiorespiratory system because this is half of that system. Right, so replace O2, remove CO2, and regulate acid bases. Ventilation, right? So this is the mechanical process. This has nothing to do with oxygen being used or carbon dioxide being moved. This is just the mechanical portion. But obviously, if we increase ventilation, there are chemical reactions to it that occur. Next is diffusion. So diffusion is areas of high concentration to an area of low concentration. Here you can see just the graph of the way respiration works and how we get oxygen into our cells and used combined with the cardiovascular system. organs, right? So alveoli is where all the gas exchange occurs. They are one cell thick and make it easy for it to cross over. The major muscle of inspiration is the diaphragm, and at rest, expiration is usually going to be just the diaphragm relaxing. But whenever we are exercising very intensely, you'll see the transverse and the rectus abdominis are part of forced expiration. Right, so we have the respiratory zone and the conducting zone. So in the conducting zone, all this is for is humidifies and filters air. And then we have the respiratory zone, which is where the gas exchange actually occurs. This happens passing the respiratory bronchioles and into the alveolar sacs, which are 300 million in number. Right, so this one, I need you guys to know, it's one of those written out ones. Be familiar with the numbers, what's occurring. Boof, 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 boof. Right, so let's go right. So here at rest, so there's no change in difference in pressure between these two, so no air is moving. Here, the atmosphere has a lower pressure, so air will come out from inside to out. And then here, your lungs have a lower pressure, so then the air will flow in. So inspiration versus at rest versus expiration. Okay, pulmonary ventilation, right? So we have tidal volume. This is the amount of air moved per breath. Breathing frequency, number of breaths per minute. When you multiply those two, we get total air moved, right? This has nothing to do with the oxygen or carbon dioxide, but just the amount of air that we actually moved in and out. And then we have alveolar ventilation, which is how much is the air actually goes to the gas exchange zone. And we have dead space, which is just that air that is in the conducting airways. Right, spirometry, right? This is how we measure the volumes and the rate of expired blood flow, like tidal volume and all those things. Vital capacity is the max amount of air that you can expire after normal inspiration. FEV1, amount that we expire at 1 second. So now once you get how much of your total vital capacity you can do it in 1 second, that gives you this FEV1 over VC ratio. So somebody with greater than 80% is normal. Somebody with less than that would be what's called usually has like some sort of respiratory disease, and usually that's going to be like COPD. Give me a second. Make sure I'm not missing anything. Tidal volume. Okay. Next. Right, so partial pressures. Be familiar, right? So alveoli air is about 100 millimeters of mercury. PCO2 is 40. Once we get it into the blood, approximately also 195, just kind of round up to 100, make it easy for you to remember. Goes into tissue fluid where it's able to dump off very easily, 40, and pick up CO2, 46, right? So this is higher pressure to lower pressure, and then this one's higher pressure to lower pressure. So then you have the deoxygenated blood over here, which is at 40 and 46, so it's dropped off a lot of oxygen, when it was here, and picked up some carbon dioxide. It goes into the lungs. We expire some of that oxygen, come back over again, and we repeat the process, right? So oxygenated blood, approximately 100 millimeters of mercury. Um, and let's look at blood flow to the lung, right? So this is ventilation perfusion. So this is the perfusion portion, right? So at rest, most of the blood flow is to the base of the lung. Kind of already went over that in class, right? It's easier to push blood down because it works with gravity as opposed to having to push it up. Mm, Yep, covered that. Ventilation perfusion, right? So it's ventilation versus perfusion. So if something is underperfused, that means it has more ventilation than it does perfusion, right? So that's a perfusion of, wait, hold up, is this one correct? Ventilation perfusion, yeah, no, this is the opposite way around. One second. Discard. Right, there it is. Oh, let me switch this over. Yeah, so something that is underperfused will have ventilation being greater than perfusion, so that makes it ratio of greater than 1, and the opposite way, something that's overperfused will be less than 1. Um, During exercise, this number gets closer, but they're still not equal. At high intensity exercise, it is very unequal as well. But overall, we're still able to work pretty well. Oxygen, right? Most of the oxygen in our blood is transported through hemoglobin, right? Oxygenated hemoglobin is oxyhemoglobin. Deoxygenated is deoxyhemoglobin. Um, see. All right, so oxyhemoglobin dissociation curve. So this is how readily hemoglobin is ready to dump off oxygen, right? So there are a couple factors that affect it. So decreased pH equals rightward shift. Increase in temperature equals rightward shift. Um, Increase in 2,3 dpg, which is what happens during altitude exposure, also causes a rightward shift. Essentially, all of these cause oxygen to be dumped off at a faster rate, which is important, right, during exercise when we're hotter, when we have a lower pH, and then in altitude where we have low oxygen content, we want to increase the amount of oxygen that we're dumping off. So here you see at lower acidity or lower pH, higher acidity, we'll be dumping off way more oxygen than at rest, right? So doing about 20% more. And as opposed to the other way around, when we're too basic, we're dumping just about 10% less. Pretty bad handwriting, sorry about that. Same thing with uh, being hotter. So whenever we're hotter, we're dumping off at 40, we're dumping off about 50% of our oxygen, while at rest, we're dumping off only about 25 to 30%. So being a little bit warmer and having a lower pH can help. O2 transport shuttled by myoglobin, right? So now we get it to the myoglobin portion, right? So now we have the oxygen in the tissue fluid. So now we have to get that tissue and, that oxygen and pump it into the mitochondria and into the muscle itself. What is responsible for that is myoglobin, right? So myoglobin picks it up, right? But myoglobin works at a much lower PO2. So at 40, which is where it's picking it up, it must be able to retain 100% of the oxygen and take it to where it's needed. So your muscle works at very low PO2, somewhere around this area of single digits. So this is about 10. So in the single digit area. So at 5, once it gets to where it needs to be, it dumps off all its oxygen, goes back and picks it up, and then repeats the process, providing a lot of oxygen for our body. Next, CO2 is mainly transported as bicarbonate in the blood. Incremental exercise. So as we continue to increase, our ventilation will increase. PO2 in an untrained subject is maintained within 10 to 12 uh, millimeters of resting value, right? So it does move a little bit, but we're still able to maintain it for longer periods of time. Already went over this. Passive usually, right? So the first muscle drive of the respiratory system comes from the respiratory control center in the medulla oblongata. Input to the respiratory control center, right? So be very familiar that the central chemoreceptors sensitive to PCO2 and hydrogen ion, right? So they're located in the medulla itself, right? So essentially the blood that's going to the medulla is being sensed by these chemoreceptors, and then from there, cerebrospinous fluid, cerebrospinal fluid, and then from there they grab the signal. Mm, So training does not alter lung structure, right? So lungs are generally overbuilt. The only adaptation that we really do get is that we have more blood and that our respiratory muscles work better, but that is not a direct increase in what's it called? In the lung structure itself, right? Does pulmonary system limit exercise performance? So no, it does not. But there is something that happens that's very weird in athletes. Oh, wait, give me a second. And they have a portion where they suffer hypoxemia, right? All that means is they have much lower PO2 values, somewhere to 20, 30 below their normal values. Uh, there's nothing wrong with that, just I guess an adaptation that may have developed or something different that happens depending on the person. And let me make sure I covered everything, didn't miss anything. Yep, yep. Yeah, I think I got everything. Um, yeah, remember with the hypoxemia, what happens is they think it happens in these people not because they have COPD, but rather because there is a fast transit time. So their blood is moving too fast that it's not able to pick up as much oxygen as it usually does. So that's why they have lower partial pressure of oxygen. But yeah,